Dear colleagues, ladies and gentlemen, I have the pleasure to open the first session in the afternoon, which is titled Lecture Session of German Ophthalmologists, and it is my pleasure to announce Professor Jonas with the title Epidemiology, Histology and Etiology of Myopia. Professor Jonas, please.
Dear Chairman, ladies and gentlemen, it is a great honor and pleasure for me to be here. Myopia is becoming one of the most important topics in ophthalmology, and particularly in East Asia. The reason is that the prevalence of myopia is deeply increasing. For example, in the Beijing Eye Study 2001, the prevalence of myopia was about 1.5% in the population with an age of 40 plus years. But already in this elderly population, degenerative myopia was one of the most common reasons for visual impairment and blindness. In a larger study on 560,000 elderly people in the rural region of the district of Beijing, myopia was responsible for low vision in overall of 0.5% of the whole population. And this was just the elderly population with an age of 55 plus years. In contrast, in central rural India, in a population-based study, the prevalence of myopia was much lower, 0.4% compared to 1.6% or 3% in Beijing. And again, in contrast, in the young generation in Beijing, the prevalence of myopia went up to 80% in the children with an age of 18 years. So that the parents are not, but the children are all myopic. And the younger the study in China, in children, the higher is the frequency of myopia, showing the steep increase in the prevalence of myopia in the younger generations. In other studies, factors associated with myopia in children were clearly the level of education in the parents and in the children, and in particular, the amount of time spent indoors or outdoors. The more time spent indoors, in the houses, the more myopia, and the more time the children spent outdoors, the less myopia. For example, in the Shandong Children Eye Study on more than 6,000 children, again, the prevalence of myopia went up to about 80% in the children with an age of 18 years. And there are now more than 20 studies clearly showing that it is most important the ratio of indoors to outdoors time spent for the development of myopia in the children. Also in longitudinal studies, children who spend more time indoors have a higher risk to develop myopia or to progress myopia in the study period of 2 or 3 years. And again, the factors associated with the progressive myopia were not only female gender, but in particularly the level of education. That means the higher the school type, the more myopia, and again, the more time spent indoors. We then wondered, how may it be in China where one goes to a very rural region into an oasis in the Gobi Desert, in a city called Echina with a population of 20,000 people, where the next village is located in a distance of 400 kilometers. But also there, in the school children, the prevalence of myopia was 80% in the 18-year-old children. And more importantly, the prevalence of high myopia was 10 to 20%. And this may be frightening, because we know that high myopia is a risk factor for maculopathy and blindness. And if this high number of high myopic children get older and further increase their myopia, the fear is that these children, then adults, may have a high risk to get blind due to myopia. So that if that assumption is true, myopia may become the most important ocular disorder, if the assumption is true. But we went back to the Beijing eye study then and thought, if indoors-outdoors is important for myopia, one may perhaps find a correlation between people who should have gone to school but who could not go during the first years of the Chinese Cultural Revolution. And indeed, the adult people who were young and should have been school children at the beginning of the great leap forward, but could not go because the schools were closed, were less myopic than the people before and afterward. Then there may be other factors associated with the development of myopia, and of course it may be genes. But large studies on 30,000 or 50,000 blood samples, where one had done a whole genome analysis, revealed about 30 genes which were associated with myopia, but all these genes explained less than 5% of the whole variation in myopia. That means under normal conditions, the genes are not important. Myopia now is not only bad, because several studies have shown that myopia is protective against age-related macular degeneration and also protective against diabetic retinopathy. The reason for that is unclear. However, myopic eyes, which are larger, have normally a lower concentration of vascular endothelial growth factor. And the vitreous is more fluid. So that the turnover of this cytokine, which is responsible for AMD and diabetic retinopathy, may physiologically be lower in large myopic eyes. Then the question is, where is the cutoff between normal myopia and high myopia? If one defines high myopia with an enlargement of the optic disc or enlargement of parapapillary atrophy, then the value is about -8 diopters or an axial length of 26.5 millimeters. As shown here, beyond that cutoff, parapapillary atrophy strongly increases. The myopic retinopathy now can be differentiated into different grades. Grade 1 is just fundus tessellation, as shown in this example with a higher degree of fundus tessellation, where one can see the large choroidal vessels. Stage 2 is a diffuse chorioretinal atrophy. Stage 3, punched out lesions of chorioretinal atrophy. And stage 4 are these punched out lesions, chorioretinal atrophy in the macular region. In addition to lacquer cracks, myopic choroidal neovascularization with bleeding, or a Fuchs spot as a scar of a macular hemorrhage. And this stage goes usually from stage 1 to stage 4. We were then interested to address the histology of these chorioretinal atrophies, which are different. Here we see the large choroidal vessels. Here we can only see sclera. And looking on the histology, one sees that some eyes have a hole in Bruch's membrane. Here is the end of the retinal pigment epithelium. Here is the end of Bruch. And here is a hole in Bruch's membrane without choroid, without RPE, and without photoreceptors. Only the inner retinal layers are present. Also here, a hole in macular Bruch's membrane. This hole can also be seen by OCT. From here to here is a defect in Bruch's membrane, and also from here to here. And macular Bruch's membrane holes have become a hallmark of myopic retinopathy. Another feature of myopic retinopathy is fundus tessellation. It can be graded from 0 to 3. In the Beijing eye study, it was associated with a number of factors. The most important one was axial length. A high degree of fundus tessellation was characteristic of a very thin choroid, a leptochoroid. So that if you don't have OCT, but see fundus tessellation, we can assume that the choroid is thin. The choroid gets thinner, the more myopic the eye is. Here minus 19 diopters. And there's another change in myopia, that's the enlargement of the optic disc, leading to a secondary macro disc. The problem is here that the secondary macro discs have an increased risk for glaucoma at a normal intraocular pressure, so that one can easily overlook glaucoma in highly myopic eyes. And it is not axial length, probably, which is important for glaucoma in high myopia. It is the enlargement of the optic disc, which is the main risk factor for glaucoma at normal IOP in high myopia. The reason may be the elongation and stretching of the lamina criprosa, so that the lamina criprosa gets thinner. The distance between the intraocular pressure compartment and the retrobulbar brain pressure department decreases, so that the pressure gradient gets steeper. Because studies have suggested that the intraocular pressure, the orbital cerebrospinal fluid pressure, and also the thickness of the lamina may be important parameters for glaucoma susceptibility. Also in the parapapillary region, there are changes. This is the peripapillary scleral flange, D, which makes out the inner 50% of the sclera and continues to the lamina criprosa, while the outer 50% go to the dura mater. In high myopia, the scleral flange is 10 times longer and the thickness is reduced to 10%. This may be a clear anatomical factor changing the biomechanics of the lamina and perhaps increasing the glaucoma susceptibility. This brings us to the zones in the parapapillary region, which are important for myopia. This is an eye with glaucoma without myopia. We see here between 1 and 2 a region where Bruch's membrane is present but no RPE. This is the so-called beta zone. Bruch membrane, yes, but no RPE. In the periphery is alpha zone with Bruch's membrane present but irregular RPE. Then myopic eyes have a zone where Bruch's membrane ends before the optic disc starts. This would be gamma zone, where Bruch's membrane is not present. And the gamma zone is strongly correlated with axial length, but not with glaucoma. Why beta zone is correlated with glaucoma, but not with axial length. So that the differentiation between beta and gamma zone makes clinically sense. If now gamma zone is very long and thinned, it may be called delta zone in the highly myopic eyes, a special form of gamma zone. And this can also be seen by ophthalmoscopy, where this is all gamma zone without postmembrane, but here we see this line. This may be the merging point between the dura mater and the sclera. Here is the peripapillary scleral flange, and behind is cerebrospinal fluid. So that this is a summary of alpha, beta, gamma, and delta. And delta strongly correlated with high myopia. And another morphological feature of high myopia are the peripapillary intrachoroidal cavitations, usually at the inferior part of the optic nerve head, characterized by an orange-like color, showing a separation of the sclera from the choroid, perhaps because the dura mater of the optic nerve is pulling it backward. Finally, one thought, what can we learn from anatomy about the process of emmetropization and myopization? And just summarizing recent anatomical findings or old ones, that it's number one, the sclera gets thinner the longer the eye is. Scleral thinning is most marked at the posterior pole, but not at all present at the ora serrata. So that scleral thinning takes place only in the posterior hemisphere. Scleral volume increases from birth to the end of the second year, but then it remains constant. So that axial elongation does not lead to more sclera, just to a remodeling of sclera. Choroidal volume in children with an age of 5+ years also is independent of axial length and independent of age. Both findings suggest that neither sclera nor choroid are actively involved in the axial elongation process. The thickness of postmembrane is independent of axial length at the posterior pole and at any other location. This was an unexpected finding, suggesting perhaps that postmembrane is a driving force to make the eye longer. Postmembrane in secondary high myopia due to congenital glaucoma is significantly thinner than in primary high myopic eyes, again pointing to postmembrane as a driving force in primary myopia. The distance between the disc and the fovea increases with axial length. However, the length of macular postmembrane is independent of axial length in emmetropic and myopic eyes. So that the increased distance between disc and macula develops only by the development and enlargement of gamma zone, where no postmembrane is. The density of the RPE cells in the periphery decreases with axial length. In the center, it is constant, corresponding to the normal length of postmembrane and normal thickness of the retina in highly myopic eyes. This leads to several speculations. First, the eye grows from birth on to the end of the second year, spherically by increase in volume. Then the anterior segment remains constant. The length of the optical axis is then adapted to the optical properties of cornea and lens. This axial elongation occurs by elongation of postmembrane in the mid-periphery, leaving postmembrane in the macula untouched, so that the density of the photoreceptors and RPE is normal explaining that highly myopic eyes can have a perfect vision. This moves postmembrane into the center of research and gives sclera a secondary role in axial elongation. It may be that postmembrane is a driving force making the eye longer, compressing the choroid, and explaining why the choroid becomes so thin, and the sclera thins secondarily. This also explains that the disc fovea distance gets larger, but not by an elongation of macular postmembrane, just by the development of gamma zone, which makes sense because one wants to have best visual acuity independently of the axial length. Postmembrane is thin, just 5 micrometers, but biomechanically much stronger than the sclera with reference to the thickness. And if one takes a pig's eye and opens the sclera, one needs quite some force to compress the eye before postmembrane and the choroid burst. So that postmembrane may be the target, and postmembrane is produced by the retinal pigment epithelium. And if that's the case, the final question was, which molecule makes the RPE produce more postmembrane in the periphery to make the eye longer? And if you know the molecule, then perhaps one could think about a medical therapy to prevent further axial elongation. And in an experimental study in guinea pigs with experimental myopization, the intraocular injection of amphiregulin, which is an epithelial growth factor family member, resulted in a dosage-dependent reduction of axial elongation in the study eyes as well in eyes without myopization. And that fits with the speculation that the RPE is a target, because the RPE has receptors for epithelial growth factor. So that as speculation, the myopic elongation occurs not only in the mid-periphery and is not only caused by a stimulus to the RPE, but perhaps as speculation, the RPE may be stimulated by an epithelial growth factor member molecule. Theoretically, this may give the potential to use it for the prevention of myopia. Thank you very much.
So, thank you for these interesting insights in myopia and glaucoma. Are there questions from the audience? You made one hypothesis in the beginning of your speech concerning the protectiveness of myopia to AMD. So if you could choose, how myopic would you like to be not to get an AMD?
-2.
Okay. Any other questions? Thank you very much.